my God, thank you today. Oh, yeah. And I thank you tomorrow. For your love, I thank you, my God.
Hey everyone, this is Dr. Collins again. Hope you're all holding up pretty well. So today we are going to start the last new material, that is regression. So we're going to start with some really basic bivariate regression, and then in the future videos we'll do some on what's called dummy variable regression. We'll do one about assessing model fit. That one's going to be nice and short for you. And then we're going to dive a little bit deeper into multiple regression, which is, of course, what your final project is supposed to be. I'm going to be providing a lot more guidance on that final project in the coming days, so stay tuned for that. Hope you're all holding up well. This is going to be probably the longest video of the entire semester, so obviously feel free to take a break, go to the restroom, pause, go grab a snack. I myself have been really thoroughly enjoying the Utz hot and spicy chicharrones. So they're really good. They're nice. They're keto friendly if that's your deal. But otherwise, they're low carb. They're kind of fun, and they're tasty. So just a couple ideas. All right. So today, like I said, we're starting with regression. We're going to be doing some basic bivariate, that is two variables, one dependent, one independent variables. Regression. Now, this is a linear regression that we're going to be talking about. I put post-apocalypse week. Who knows, because I've lost track as well. All right, so the cover for today's slides is the Rwandan parliament. And that should become obvious throughout, but the basic gist of it is Rwanda has the greatest share of women in its parliament. 63% of its parliament is made up of women, which you can see from that photo, right? Lots and lots of women there. From a variety of backgrounds. So the color theme for today, the color scheme for today will be the colors of the Rwandan flag, this blue, green, and yellow. And of course, the music at the beginning and end of the slides will be by a Rwandan recording artist named The Ben. So if you're interested in that, certainly check him out. Cool. So moving on. Here are the topics for today. So we're going to start by talking about this idea of prediction. Now, your textbook frames regression around its utility as a predictive tool. I don't know that that's really the best way to frame regression or the usefulness of it. However, I do think that it's one way you can do it, and it's the way your book does it. So I think that's a useful way to start things out, kind of a nice way to combine the book with these lectures. Then we'll look at some scatter plots. All right. Now, as you recall, when I talked about correlations, right? One way that we can display a relationship between two variables in a scatter plot is with a best fit line. That'll lead us into a nice discussion of what we mean by a linear model. And then we'll run through our steps. Okay, we'll end with a preview of what's to come. So here you see, based on as of late 2018, as of December 2018, here are the top countries in the world where women make up a share of the lower house of parliament. Rwanda is, of course, highest at 61%. It's actually up to 63% now. Cuba is at 53%. Bolivia was at 53%. US, obviously, all the way down at 75%. All right. So, diving in. The utility of prediction. Now, prediction is interesting in that it allows us to create what's known as an out-of-sample prediction. We can predict beyond what we observe, all right? But let's take a step back for a second and think again about correlations. Correlations, at their heart, tell us about how much of the variation between two variables is shared, okay? Now, what if we know the value of one variable for some new observation, and we want to know what the other one might be? Okay, we want to know what the value for that variable, for that observation is for the other variable. Correlation can't do this for us. There is actually technically a way you can do it, but the correlation we've been dealing with is not very good for that purpose. However, regression does allow us to do this. Okay, it sets up a model such that knowing the value of x can yield a probabilistic prediction of y. And of course, as I've mentioned, we're going to be using the linear model. All right, so if you take the equation for a line that you're all familiar with, y equals mx plus b, right? And you know the value of x, and you've estimated the values of m, the slope, and b, the intercept, then you can calculate a predicted value of y, okay? So that's the kind of regression we're going to deal with, linear regression. There are nonlinear regression forms, okay, that we'll talk about as sort of a closing of all this discussion of regression. Now, starting with a scatter plot. Here is a scatter plot with data from the VDEM project, Varieties of Democracy. This is their version 10. So this is 2019 data on 173 countries. It's the percent women in the lower legislative chamber on the y-axis. All right, so you can see there the y-axis, percent women in the lower legislative chamber. And if it's unicameral, then it's the only legislative chamber. And they've created a variable called Women's Civil Liberties Index. So are women granted the right to vote? Are they allowed to own property? So on and so forth, right? So a lot of countries will score very highly on this, as you can see up here. And then, of course, you've got countries like the People's Republic of Korea, otherwise known as North Korea. All right, that's way down here. Okay, so you can see that there's a lot of variation here. Okay, now, there's the U.S., right? Just wanted to single it out so you can get some gauge of where the U.S. falls. We're slightly above 20% in terms of representation in the U.S. House. And of course, we're right around 0.9 on Women's Civil Liberties Index. Few countries above us. No one's a perfect one on this, even though it's rescaled. No country's a perfect one. Denmark, you can kind of see there as DNK. Denmark is pretty high up there on that. But generally, right, we do see some general trends here. And you could probably think already there's a general positive increase here. Okay. You see, of course, Rwanda is way up there. Rwanda is one of the more advanced countries in terms of women's representation. They have a very robust gender quota system. That's one reason. Okay. Now, if all we were doing was looking at the correlation coefficient, right? Remember, we represent that with that lowercase r. The correlation coefficient is 0.255. So it's a moderate correlation. But I put the star after it. That tells us that it is, in fact, significant at p is less than or equal to 0.05 in a two-sided test, in a two-tailed test. Okay, so that's what that means. So there is a correlation here, and it is statistically significant, which of course means that if the population correlation were truly zero, our sample would be very unlikely to yield a correlation coefficient of 0.255. Okay, so again, a correlation tells us how much variation the two variables share. But how else can we represent this relationship, right? Think back to that correlation discussion that we had several weeks ago, right at the beginning of the online class. We could do this with a line, okay? So if we wipe out the regression or the correlation coefficient and we drew a line, okay? In fact, as you'll see, the title changed. It's now we are applying what's known as a best fit line. This line does represent the best fit of the data. Well, what does that mean? Okay. Think about it this way. All right. In fact, let me go back. Hang on. Sorry. All right. So we've applied our best fit line. What does that actually mean? Go ahead and take a look at Ethiopia. All right. Ethiopia is right here. Now, Ethiopia, you can see how far away it is from our best fit line. Now, if a line is a prediction, any country that has a Women's Civil Liberties Index value of 0.42, as Ethiopia does, we would expect to have around 20% women in its lower chamber. But in fact, Ethiopia is about double that, right? So Ethiopia, we didn't get that one very right in our prediction. Similarly, if we look at Yemen, right? Yemen, they have a Women's Civil Liberties Index of just under 0.2. We would expect them to have around 18% women in their lower chamber. But in fact, they have zero. They have no women in their lower chamber. All right. So as a result, okay, we can see that there's another error term here. Sometimes we'll have errors above the line. So Rwanda is a really high outlier here, right? It's a really high error. In fact, Cuba is a really high error here as well. Burundi is another example of a really high error. And then we've got some really low errors, Vanuatu, for instance, okay, down here. All right, Benin right here, Japan, actually. The US, we're actually pretty close, right? The prediction, the difference between our predicted value and the observed value for the US is pretty close, okay? So a best fit line means that what we're seeking to do is minimize that error as much as possible, okay? So we're trying to collectively minimize that error. Now, technically what this means, the formal way that we talk about this, is that we have minimized the sum square of errors, okay? So if you think of this line as an error and this distance as an error, and you do that for each individual data point, each individual observation, you say, okay, how far off in our prediction of y are we for each of these points, all right? You square those distances because you don't care whether you're below the line or above the line. Right? All that matters is you're far away from the line, like in Rwanda, or you're pretty close to the line, as in the Dominican Republic right there, okay? Now you square them and you add that up, all right? The point is, this is the straight line that we can draw that minimizes that total sum of squared errors, okay? This is one technique for running a regression. All right, and that technique is the ordinary least squares regression, OLS. All right, there are other ways you can estimate linear regression. There's the general model, generalized linear model. That's fine too. OLS is sort of the gold standard. Right, that's the one we're going to focus on. It's also probably the most intuitive of all of them. All right, so we can see there, right? We have all these error terms. You cannot draw a line for which the sum of squared errors is less than it is for this line. It's not possible. You cannot draw a straight line that fits these data better by that definition, okay? So that's what we're going to try to do today, okay? So let's dive in. Now, in linear regression, what we're doing is we're assuming the relationship between these two variables in the population is linear. Now, what do I mean by linear? Well, it means it's always traveling in one direction, right? A line doesn't turn, right? It keeps going in the same direction, whether as x increases, y increases, or y decreases. But there's no inflection point, right? It doesn't turn at any point. It's a straight line. It's going in the same direction. It's unidirectional. Also, the relationship doesn't depend on the values of x, right? If x equals 1 to x equals 2, the change in y is going to be the same as the change in y from x equals 3 to x equals 4. That might not be the case with an exponential, right? Where for low values of x, there's very minimal increase in y, but the higher you go on x, the stronger the relationship gets. Or of course, in a curvilinear, like a parabola relationship, right? So in a parabolic relationship, your relationship between x and y might be positive down here, then negative over here, or vice versa, right? If the parabola looks like this, okay? That's not what we're looking at. Now, of course, this requires that we assume the relationship in the population is also linear. There are, of course, times this might not make much sense. If you look at a scatter plot like we just did, and you see a clear curvilinear relationship, then you might know that a linear model might not be the best fit for your data. There are ways to deal with that, okay? But for our purposes, we're going to focus on a linear relationship, okay? So we'll start by discussing bivariate relationship. What do I mean by that? Two total variables, one independent, one dependent, okay? Two variables, that's it. That's bivariate. Contrast this with multiple regression, where you have lots of independent variables. That's the one we're going to be doing for your papers, for your projects for the end of the semester. And on the other hand, you've also got something known as multivariate regression. So we have bivariate. What you're doing for your projects, where you have lots of independent variables and one dependent variable, that's called multiple regression. Multivariate regression is when you might have many dependent variables, okay? That's much more advanced than we're going to get into in this class. So continuing our discussion of this linear model, think back to your days in algebra, and I've already mentioned it. What is the formula for a line? Well, it's very straightforward, right? It's y equals mx plus b, right? Y is your dependent variable, x is your independent variable, m is the slope, the relationship between x and y. As x increases by 1 unit, y increases by however many units. Okay? It's the slope. And if you recall what a slope is called rise over run. It's sort of the common mnemonic device that we use to remember what a slope is, right? So for every 1 unit increase in x, there is an m unit increase in y. So if your slope is 3, you go rise 3 over 1. So for every 1 unit increase in x, you get a 3 unit increase in y. That's important. We're going to come back to that later. Okay? And I just talked about that. Now, what we do is we impose this model on our population of interest. Right? We're assuming that this relationship is linear. Now, if ultimately it's not linear, then we will not get good results. We won't get accurate results. All right? Our test won't be valid. We're not actually testing what we think we're testing. Okay? So it's important to consider whether or not that relationship is linear. Rarely is the true relationship truly linear. I want to mention that now. But unless it's like curvilinear or parabolic or exponential, a linear model tends to do pretty well. Okay? So all models are wrong. Some are better than others. Okay? We use slightly different notation, however. All right? Now your textbook uses just y and x. It doesn't index them with the I. I index them with the I because it reminds us, right, that we're looking at a variable that has multiple observations. All right? So for any observation y, that's going to be equal to some alpha plus beta x. Okay, where x is the same observation as y. Now, alpha is the intercept, which is b in that earlier one. Now, your textbook, instead of using alpha and beta, uses a and b. I use alpha and beta. Okay, I think it's going to be a little bit clearer why I do that. All right, but for our purposes, just get used to seeing alpha and beta. Alpha is the intercept. What is an intercept? Well, it's simply the value of y when x is equal to 0. All right, so if x is 0, where does that line intersect the y-axis? Okay. Beta is the slope. All right, but from now on, we're not going to call it the slope. We're going to call it the regression coefficient because that's what it is. Okay. When we talk about regression coefficients, when you see those things in tables and articles you've read for other classes, all you're looking at are estimates of the slope of the line that represents the relationship between that x and that y. Okay? So, diving in a little bit further, now, because we're studying a social science, which deals with people, and people are messy, there's rarely going to be an observed y that falls exactly on our predicted line. Right? Think back to that scatter plot we just did, right? There were a couple of points that were almost exactly on that line, but the vast majority of them weren't on that line, right? Because we're dealing with countries and people and governments, and it's the best fit data. It's not a perfect fit. If you get a perfect fit, there's probably something wrong with your data, okay? Which means there's going to be some uncertainty or some error. It's another way of saying uncertainty. So we have to represent that somewhere. Now, in our model of the population, we say that y is equal to alpha plus beta x plus u. U is our error term. All right, so think of it this way, right? For the US, we were pretty close to that line. U is going to be very small. For Ethiopia, that was a very big error. U is going to be very big. For Rwanda, it was huge. For Yemen, it was big. All right? So our U term there is going to be pretty big. But in the population, generally we say, all right, here's some line. It intersects the y-axis at this point, alpha. The slope is beta. And then there's going to be some error. Okay? So for each individual observation, I, the value of y is going to be a linear function of x, alpha plus beta x, plus some error. That's all that is, okay? So alpha plus beta x is the systematic or predictable component. You can plug in a value of x and spit out a value of y. U sub I, that error term, is what we call the stochastic component or random component, okay? So we need to estimate these population parameters. That's the whole goal here, right? We want to estimate beta, the regression coefficient, the effect of X on Y. So what do? We put little hats on them. That's it, okay? So our estimate of population parameter alpha is alpha hat. Our estimate of population parameter beta is beta hat. Our estimate of population parameter U is U hat. That's it, okay? So we need to estimate these population parameters. And again, the hats just tell us their estimates obtained for our sample. That's it. Okay, so hopefully you're with me. So again, alpha plus beta X is the systematic component. That's the predictable component, okay? Because that's the line itself, right? That U is not predictable, but it should be random, right? If you go back and look back at that scatter plot, in fact, I'll go ahead and do that for you now. If you look at this scatter plot, let me pull up the one with the line, all right? You can see there that you've got lots of points above the line, lots of points below the line, but it doesn't seem systematic. It's not like most of the points are above the line or most of the points are below the line, okay? It's fairly randomly scattered about that line, okay? So, continuing. Oop. Now, we can now predict the values of Y based on values of X. So our estimate of Y, that's Y hat, is equal to alpha hat, what we obtained from our estimation, plus beta hat, which we obtained from our estimation, times that value of X. So you plug in a value of X, and you've calculated alpha and beta, which we'll do later, and then you can get a predicted value of Y. All right, so if Y is equal to 1 plus 2X, and X is equal to 5, then what's Y? Well, 5 times 2 is 10, plus 1 is 11. So if X is equal to 5, you would expect Y to equal 11. You would expect Y to equal 11. So this is really our expected value of Y given some value of our independent variable X. That's all that means, right? Expected value of Y given, that's what that vertical line means, given X, I is equal to alpha hat plus beta hat Xi. That's all that means. Okay, so that's what we talk about when we talk about linear predictions. You can predict a value of Y with some new variable value X. Okay? Now, note that our prediction of Y excludes that error term, because in a prediction, we don't know what the error is going to be. It's going to be random. Okay? But our prediction is just going to include that. So if we have a data set, we use that data set to calculate or estimate beta and alpha. And then we say, all right, along comes some new observation. Let's say some new country is created. They get a civil liberties score for women. We can attach a value to that. And then we estimate what their intended or estimated or expected value of the percentage of women in the lower chamber should be. All right. So that's what we do. Okay. Now, again, we don't need to include U here because we expect that error term to be random. Now, around the regression line, as I said, we should see some random fluctuations. If it looks like the spread of observations around X, around the line, is greater or less, depending on the value of X, so let's say it looks like a filter or a cone going in one direction or in the opposite direction. Okay? If it looks like that, we've done something wrong. It means that our model doesn't properly fit the data. Okay? We'll talk about that later. All right, but for now, don't worry too much about that. So let's go ahead and calculate. Well, let's frame it in terms of the steps. Okay, so with the steps, we start out by defining the null. We set the threshold for significance. We select the appropriate test statistic. Hint, it's going to be regression. All right, then we calculate that sample test statistic. And then we determine the critical value needed, compare it to the critical value, so on and so forth. The steps you're all familiar with. And of course, right, we're dealing with Vassar stats or SPSS, which gives us a p-value, right? I'm not going to make you hand calculate regression coefficients. I'm going to show you how, but I'm not going to make you do it. So what does that mean? It means that SPSS is going to give us our p-value. We don't need to worry about t-tables anymore. All right? You're still going to need that for your exam. I'm going to want you to be able to do it. However, I'm going to make sure that for your projects and the like. I'm not going to make you go back and forth and compare your t-value to a t-table to get a critical value. You don't need to worry about that. Okay. Instead, you can just report the two-sided significance reported by SPSS. Okay. So steps 5 and 6 kind of go out. And then 7 and 8, if it's above 0.05, if P is above 0.05, you don't reject the null. So that's 8. If it's below 0.05 or equal to 0.05, you reject the null. Okay, that's step 7. So let's dive in. Step 1. Now, let's say our alternative or research hypothesis is beta is greater than 0. Okay, so again, we think more civil liberties for women. We expect that should have a positive effect on the number or relative representation of women in the national legislative lower chamber. Okay, so of course our null would be that this thing is equal to 0. We assume that this is true. We assume our null is true in the population. Now what we want to see is, based on our sample, how likely is that null to be true given our sample? Okay. Now we also set the preferred significance level. Again, it's almost always going to be a two-tailed p-value of 0.05 or less. That's it. We could use a one-tailed test because we have a directional hypothesis. All right. We think that B is going to be greater than 0. All right. If we had just said that B is not equal to 0, then that would be a non-directional hypothesis. Now, we may eventually add other variables without directional hypotheses, so it's good just to stick with the two-tailed test. That's going to be sort of the standard test to use. But you will see papers that report P equals 0.10 or P equals 0.05, one-tailed P equals 0.10, two-tailed. Those are unidirectional hypotheses or directional hypotheses. Okay. Now we need to select our test statistic. So if you have an interval or ratio dependent variable, this is that flow chart that I showed you. Okay. So if you have an interval or ratio dependent variable, how many independent variables do you have? Well, for now, we're only going to work with one. Now, you could use dummy variable regression if you have a nominal independent variable. We'll come back to that. Or you could use bivariate linear regression. Now, if you have multiple, then you would use multiple regression. We are going to focus on this middle one. Okay, focusing only on bivariate linear regression. Now we calculate it. Remember our goal, minimizing those errors, the distance from the line for each observation. That's what we want to do. Here is the equation your textbook gives you. I know, right? That's pretty ugly. Bear with me. This is really ugly, I agree, but we can rework this using some kind of complex algebra. Doing algebra with some notation, summation notation, can be kind of tricky, so I'm not going to walk you through it step by step. We'll end up with something that looks like this. Okay, this is another way to calculate it. Mathematically, they are identical. All right, I promise. You can run your own numbers with this if you want to. It's the same damn thing. Okay. Now, still looks a little bit tricky for some of you, I'm sure. For most of you, I expect that. But look at the numerator of this second equation. If you remember back to when we talked about correlations, you start the correlation by looking at the covariance. And the covariance is literally the same numerator, except it's divided by n-1 instead of this. Okay? So basically, how much variation do they share together? Right? So x's distance from x and y's distance from y. If they're both really high, then that numerator is really big. They've covaried together. All right? Make sense? Now, if one deviates in one up and the other deviates down, then they're negative. Right? You have a positive number times a negative number, that's negative. So if on balance, you have a bunch of negatives, then your slope is going to be negative. Make sense? That denominator is a little weird, though. The denominator is actually a measure for the spread of x. It looks kind of like a standard deviation. Right? Think about the numerator for a standard deviation. It's just that, and then you divide. It's just this, right? This denominator here is the numerator of a standard deviation for x. okay, or actually the variance, because we haven't taken the square root of it. Now, what this means is that for a given covariance between x and y, the slope increases as the spread of x increases. The bigger the spread, or as the spread of x decreases. Sorry, I really should have made that clear. So if you have a relationship that looks like this, but then you compress that x-axis, that thing's going to go like this. If you just push them all together, that line's going to get steeper. Right? Think about like balancing. I don't have a pen or pencil in here. Actually, I do have a marker. So let's say you have a marker, right? Let's say this is your line as of right now. Okay. If we compressed, it would look more like this. Okay. Now I know that's kind of a weird thing to think about. If we compressed our x-axis, brought it together, that line would increase in slope. Okay. That's all that means. All right. So if x is really spread out and the relationship is like this, that's different than if you still had the same values of y, but x were more compressed. Okay? That's all that is. Again, I'm not going to make you calculate this stuff by hand, but it's just giving you some mathematical idea of what a slope is. Okay? The shorter the run, the same distance of y, the same rise of y, you're going to see that rise over run increases. That's all this means. Okay? So if you reduce the run, then the slope will increase. Smaller denominator, larger overall beta. So we do need a test statistic because we want to know whether or not our estimate for beta that we just calculated is due to random chance, or if it's substantially different, significantly different from our hypothesized population parameter of 0 in the null hypothesis. So we can do that. Now, remember that t is how many standard errors away from the hypothetical population parameter of 0 our observed sample statistic is. So what do we need? We need a standard error. If you need a standard error, you have to know the variance or standard deviation of beta. I'm not going to make you calculate this. Don't worry too much. It's just this. Okay? It is the squared sum. It's the square of each of those errors. Sum them all. Divide that by n minus 2. That's it. That makes the standard error this. Okay? Don't worry about that. That's just what it is. Okay? I'm not going to worry about walking you through that. Okay? Suffice it to say that the greater the spread divided by the square root of a greater spread, that gives us our standard error. This makes t that. Really straightforward. It ends up just being our estimate of beta divided by that standard error. Okay, now what is that little n minus k? Well, that's our degrees of freedom. Okay, k is the number of parameters we are estimating. In bivariate regression, we're estimating 2 parameters, beta and alpha. That's it. So degrees of freedom is n minus 2 in bivariate regression. Now, if you include 10 independent variables, right? So you have x1, x2, x3, all the way up to x10, then you're estimating 11 parameters. All 10 of those plus alpha. We still have that intercept, sometimes called the constant, that we have to think about. Okay? So what does this mean? It means that you can get the t value simply by dividing the standard error from beta. That's it. Okay? So often in papers, all we see in published articles, all we see are the regression coefficient beta, the estimate for that, and usually in parentheses just beneath it, the estimate for the standard error. And then there's a star, an asterisk, if p is less than or equal to 0.05, or whatever significance level they've set. They don't ever actually report the t value because you don't need to. All right? Basically, if you have a large enough sample size, over say 100, right, and your t value is greater than or equal to 2, it's significant. All right, because we know that at 100, the t value we need, the critical value, is 1.98. So if your beta is twice as large as your standard error, and you have at least 100 degrees of freedom, you're going to be significant. Okay, so if beta divided by SE is 2 or greater, you will see something that is significant. Now, of course, that all depends on your sample size. Smaller the sample size, the greater your value of t, the bigger your beta needs to be relative to your standard error. Okay? All right. So again, if the DF is greater than 100, critical value is 1.984, which means that if beta is more than twice as much the standard error, you're golden. So you only really need to report beta and standard error. You don't even need to report the t. Okay? And you want to report beta. That's important. But typically papers only do that. So let's recall our example. Let's go back to that example. Here it is. Okay? Now, you can go in and you can run this through SPSS. All right? You can take these data from the VDEM. You can run it through SPSS, get this regression line here. That's the regression. All right? That's the results. The estimate for alpha is 14.1. We'll talk about how to estimate alpha in a minute. We almost never worry about alpha, but we have to do it mathematically for it to work. Otherwise, we're forcing the origin to be at 0, right? Which is weird. We don't want that. We're forcing the intercept rather to be at 0. We don't want to do that. Now, you'll see the slope of the line is 13.56. Sounds pretty big, all right? But let's think about that. Is it a significant effect? First and foremost, step 6 through 8, SPSS will return us a t-value of 3.48. Okay, that is beta is roughly 3.5 times larger than the standard error. Okay, is that significant? Yeah, it is. All right, because we have 173 observations here. We're estimating 2 parameters, which means we have 171 degrees of freedom. So as long as t is greater than 1.98, we're good. What does this mean? Well, we can interpret this as saying more civil liberties for women appears to increase their descriptive representation, and this effect is not likely due to chance. That is, we can reject the null. Okay? But how do we interpret that? How do we interpret that actual beta, that 13.56? Think back to what a slope is. Slope is just rise over run. So anything divided by 1 is itself, right? So if we say that the slope is beta over 1, that's just rise over run. So a 1 unit increase in x, that's the run in the denominator, should yield a beta unit increase in y. That's it. So what does that mean? A 1 unit increase in x. So here's our Women's Civil Liberties Index. A 1 unit increase in that should yield a 13.56 unit increase in y. And we can see that, okay? Sounds like a big effect until you consider that our x value takes values between 0 and 1. It can't go above 1, it can't go below 0. So a 1 unit increase is the maximum possible effect, okay? This is going to be important when we consider other variables, all right? When you look at the values of beta. Right, you're going to say to yourself, wow, that one's really big. Well, if x can only increase by 1, but you have another one where beta is like 0.002, but x ranges from 0 to a billion, then that can have a massive effect. Okay, so you gotta count about how important that range is. Right? You got to figure how important that range is in x. Right? So that's how you interpret that beta. A 1 unit increase in x yields a beta unit increase in y. So going from 0 to 1 on the Women's Civil Liberties Index should increase women's representation by about 13.5 percentage points. Okay? And in fact, that's the difference between this lowest point on the line and this highest point on the line. That difference is 13.56. Okay? Because we've increased by 1. Okay. Now, if this went from 0 to 10, all right, then of course you could see 135.6 unit increase in y, which would be weird because it's a percentage. You can only go from 0 to 100. Okay. So you can plug in values of x to get predictions. All right. So if you went in and you said, okay, let's say I have a country that is a 0.32 on Women's Civil Liberties Index. Well, you plug that in. 14.1 plus 13.56 times 0.32 is equal to 18.44, right? So you would expect to see, So you would expect to see 0.32. You'd expect to see it right around there, 18. Okay, right around where Turkey is and Tajikistan. Okay, so thinking forward, what about alpha? We can estimate that, right, using this. Now, your textbook gives you something different, but number one, who cares? And secondly, this is easy to show that this is mathematically identical to your book. Your book says alpha is equal to the sum of y divided by it's equal to the sum of y minus b, or beta, times the sum of x, all of that over n. Well, when you factor that sum of y over n is the mean of y, and the sum of x over n is equal to the mean of n, you see that these are the same things. The mean of x, rather. Okay, so they are the same thing. This is just an easier way to phrase it and to show it. Okay, then you get a t. Don't worry about how to calculate that. First of all, don't worry much about the intercept anyway. Okay, so alpha can be statistically significant. You can have a statistically significant estimate of alpha, meaning that, right, in the population, if you assume that alpha is equal to 0, it can be statistically significantly different from that. That's allowed. It's okay. This makes sense to interpret in our example because x can, in fact, equal 0. All right, a 0 on Women's Equality Index or Women's Civil Liberties Index, right? North Korea had a 0, so it's possible you can have a 0. Okay, but for a lot of times you can't have that. Right? Think, for instance, about, let's say you are estimating candidate vote share as a function of their height. Can a candidate have 0 height? No, they wouldn't exist. All right, so it would be stupid to interpret alpha in that case, because again, alpha is what y is equal to when x equals 0. So if x equals 0 makes sense, you can interpret it. All right, but if x equals 0 doesn't make any sense, then don't bother. Mathematically, it has to be there. That's all that means. Okay, and in fact, when you start adding in multiple independent variables, then you interpret the alpha as what y is equal to when all the independent variables are simultaneously equal to 0, which is usually impossible, if not very unlikely. Okay? So we almost never interpret the intercept. Mathematically, it has to be there. We have to report it. We report it like another variable. We just say constant or intercept, and then we list it. We list the value, the estimate of it, like we would list our regression coefficient, and then we list the standard error for it, which we can do as well, and then we say whether it's significant or not. But in the text of the paper, you never interpret it. So reviewing, that was a lot. Now we know how to handle one ordinal interval or ratio level independent variable with an interval or ratio dependent variable. Regression allows for prediction and a common sense measure of the relationship. Common sense in that a 1 unit increase in x yields a beta unit increase in y, right? The rise here is beta, the run is 1. Okay, now we don't really need to worry about calculating this one by hand. It's tough, it's arduous. Your textbook shows you how to do it. If you want to, by all means, go for it. SPSS does a phenomenal job with it. Good on you, IBM. Now, what if we have a nominal independent variable? Then we need to use dummy variable regression, right? So the easiest one, obviously, is if that's just 0 and 1, and that's your category. You have one category, right? It is this thing or it is not this thing. Then it just acts like a switch. We'll look at that later, right? But what if you have a nominal variable like religion, right? Where a 1 is Buddhist, a 2 is Christian, a 3 is Protestant, whatever, right? So on and so forth. If you have a case like that, you can't do that because a 1 unit increase in x doesn't make any sense. You're not increasing in traits of anything there. Okay, so instead we dummy them out. So we put Buddhist 0, 1, that's its own variable. Christian 0, 1, that's its own variable. Jewish 0, 1, that's its own variable. And we do the regression accordingly. Okay, we'll look at that later. What if we have more than one independent variable? Well, then we use multiple regression. So next up, we're going to be talking about dummy variable regression and interpreting something known as model fit. Basically, how well does this linear relationship, how well does that actually depict the relationship between these two variables? Okay, so we'll talk about that in the next video. That one should be much shorter. All right, thank you all, and I hope you all have a lovely rest of your week. I'll be back with the model fit and dummy variable regression. You'll have that due as well for tomorrow, for Tuesday rather. Then Thursday, I've got starting to look at a little bit more advanced stuff with regression. Then the following Tuesday, we'll finish up multiple regression. Okay, and we'll talk a little bit about some things beyond regression in that one as well. All right, I'll see you all in the next video. Keep in touch. Bye.